In the last class, we did the decoding, unique decoding of Reed-Solomon, and then based on that Walsh-Hadamard Reed-Solomon concatenated code. So for Reed-Solomon, we showed that the errors that it will be able to handle is 22% in practice. Right? So 22% of errors can be uniquely decoded in deterministic polynomial time. And Walsh-Hadamard Reed-Solomon is that will be 1/4 of 45%, which is more than 11%. Okay, so Walsh-Hadamard Reed-Solomon is a practical binary code, and there is a deterministic polynomial time algorithm to correct up to 11% of errors, which is pretty good. But for hardness amplification of worst case hard functions to average case hardness, we need stronger forms of decoding. Basically, we want to limit the number of queries we make to the corrupted string, the number of places we are querying, and that is called local decoding. So let us define it. So let E be a code that is stretching n to m. Let this be an error correcting code. And rho be a fraction between 0 and 1. So this will be the parameter associated with local decoding. Basically, how many errors can it tolerate? So a local decoder for E handling row errors is an algorithm that given so the message string X has n bits, given the jth location, it basically has to decode that bit with high probability, making very few queries. So given J and oracle to Y, such that Y is close to Ex, okay, so Y is row close to the code word E of X. That is what is given. And of course, you have to find this xj, jth bit of X of this code word E of X. You don't have to find the whole string X, not n bits, but only one bit. Output xj with probability at least 2/3 in polynomial in log m time. Okay, so the j should be output and the time taken should only be polynomial in log m. So remember, this is exponentially smaller than the length of y, which means your algorithm can query at most polylog many locations. It cannot look at the whole string y. Okay, so you could compare this with the log space computation. Okay, except we are allowing here a polynomial in log m. So for example, log m whole square, log m whole cube is fine. So in other words, when m is large, very few bits of y are needed. Okay, so this is consistent with the term local. Basically, just by using very local information about y, you are deducing xj with high probability. Remember that xj has only two choices, 0 or 1. So your answer bit should be correct with 2/3 probability at least. And now surprisingly we will show that all these codes that we defined, they have local decoders. So let us start with Walsh-Hadamard. So Walsh-Hadamard code has a local decoder for any row smaller than 1/4. So if the number of errors is less than 25%, say 24%, then any bit can be locally decoded. Let me define short term for this. LD row. Okay, this is especially helpful in Walsh-Hadamard code because that is a very long code. N bits it is stretching to 2 raised to n. And now here local decoder will only need polynomial in n many queries. Only those many bits. It will not require the whole 2 raised to n many bits. Okay, so this is especially good to know. What is the idea? So the idea is quite simple. If you want to know xjth bit, jth bit of x out of the n bits, then basically you look at the string y, this corrupted code word, randomly pick a location and pick a location that is correlated with j. Okay, it's basically just shifted by a vector which is the elementary vector, jth elementary vector. So you look at you pick a position z and pick another position z plus ej. Okay, and take the sum of those two, take the parity. That's the idea. So query two positions z and ej, z plus ej in y, where ej is jth elementary vector, which is simply flipping the jth bit in z. Okay, so it is z and z with the jth bit flipped, these two locations in y, and then you take the parity of those two locations. So output y at the z location and y at the z plus ej location. That is the idea. So let us see the algorithm. So input is some j, oracle is given f, right. So Walsh-Hadamard has 2 raised to n locations, so f is just an oracle. Given an n bit string, it will output a bit in that location of y. So oracle f such that the probability over locations of f at z being different from the actual value. Remember this inner product, binary inner product. So, z location of y is just the inner product of x and vector z, right. So, fz being wrong, fz being a corrupted bit, this probability is given to be smaller than rho, which you know is less than 1/4. And in the output what you want is, so this x is unknown first of all. And f is corrupted E of x. Okay, so f is given to you as an oracle, that is a corrupted version of E of x, the code word. X is the unknown for which you want the jth bit, right, that is your input, and output will be just a bit. That bit has to be with high probability xj. So, what is the decoder? So, the decoder will, as already given in the idea, it will randomly pick a location then it will pick this elementary vector, jth elementary vector, let Ej be the string with 1 at the jth place, and 0 in the rest. And as given in the idea, it will just output f at z plus f at z plus Ej mod 2. Right. So, the algorithm is exactly what the idea was, and now we have to analyze why it works. Why would it give xj? So, time complexity is clearly polynomial in n. Which is equal to polynomial in log m. Right, because m is equal to 2 raised to n. Now, let us do the analysis. So, over random location z, the probability that both of them are correct, f z is correct and the other location, correlated location z plus Ej, that is also correct. Or you can think of the opposite, either z location is wrong or the other location is wrong, right. What is the probability? That is at most rho plus rho. So, it is 2 rho and subtract it from 1. So, both of them being correct, the probability is at least 1 minus 2 rho, which is greater than half. Now, since both the locations are correct, what happens when you take the parity? right. So, that is equal to x plus x inner product E j, right, mod 2. This is also then probability at least half, which means that probability over the experiment, so random z, the bit being equal to x j, this is at least half. But you wanted 2/3, so you have to repeat this experiment, repeat it, let us say 3 times, okay, and then take the majority vote. So, repeating the experiment, boosts the probability. Okay, so then repeat the experiment, take the majority vote, and then output the majority as B. That with very good probability is xj. Okay, so that finishes this theorem, which is the local decoder for Walsh-Hadamard for errors up to 25%, just less than 25%. Now we have to do a similar thing for Reed-Solomon. Instead, we will do it for Reed-Muller. It will imply for Reed-Solomon. So next, do that. So recall that Reed-Muller is the map which sends L-variate polynomial to all evaluations, right? And the distance is given by this polynomial identity lemma. Distance is 1 minus degree d of your message polynomial, number of variables is L. So, distance is 1 minus d over the field size. Where the field, you will take finite field, it should just be bigger than d. In fact, you will take it to be at least twice d, so that the distance is at least half. If you take it bigger, then the distance will be close to 1, but remember this is non-binary distance. It is not, unlike Walsh-Hadamard, this is non-binary. So, to make it binary, remember later we will apply Walsh-Hadamard, right, that we have to give a different local decoder. Let us first do Reed-Muller. So, let us take this view that instead of L-variate d-degree polynomial coefficients being the domain of Rm, we will take that many evaluations. So, view Rm as mapping L plus d evaluations of a polynomial f to its f to the L evaluations. And note that L plus d choose d evaluations uniquely specifies f. because it is degree D and L variate. Okay, so L plus D choose D evaluations will uniquely give you all the L plus D choose D coefficients, hence uniquely specifying F. So we could have used either of the representations, coefficients or evaluations. Let us look at the evaluations for local decoding. It's equivalent. And with that understanding, the theorem is for all fractions rho 1 by 6 1 minus d plus 5 by size of the field minus 1. This is basically the distance divided by 6. Okay, so for any row, at most distance divided by 6 of Reed-Muller code, there is a local decoder. There is a local decoder correcting up to row errors. What is the idea? The idea will be actually a generalization of what we did for Walsh-Hadamard. So there we picked a random location and a correlated location. In the Reed-Muller case, what we'll do is we'll again pick a random point in space, right? Because this polynomial f is given to you via evaluations. So we'll pick a random location, which is actually a random point in the space, f to the L, and we'll just pick a random line through that point. Okay, so on the line we will query f. That's the idea. So that all these points on which we are querying, they are somehow correlated. So the point that we will take in space will be this point which is given to you in the input. You wanted to evaluate f at point x. Take that point x, that is a fixed point x in the space, and then pick a random line. Okay, so in a way opposite to what you did for Walsh-Hadamard. But in the end, all these points on which you are querying, they are all heavily correlated by x. So let's first give the setting. So degree D polynomial f is unknown. And a point x in the space f to the L is given in the input. And what you want is, we want f of x, field element. F is unknown, point is known, and then you want to evaluate f at x, right? It's this question. So we'll draw a random line through x in the space. That's the idea. So pick a random line Lx through x. Evaluate or query f on all these points. So what we are doing is, this is your space f to the L. This is the point x in the space given to you, and what you have done is drawn a line. Okay, that's a random line, and this is where you will query f. This is what you query, f value. Okay, so what are the f values at these points, and how many points there are on this line? Well, in the real space there would have been infinitely many points, but fortunately we are in this finite field based space. So, the number of points will only be size of the field, which is finite. So, you query small f on all these points, and from that try to learn fx, right, that is the goal. So, pick a random line Lx through x, evaluate f on each point in Lx, now remember line is like evaluate or querying f on Lx is like reducing f to univariate case, right. So, f now becomes a univariate polynomial, and that means you can invoke Reed-Solomon decoder. So, use Reed-Solomon decoder to learn f. Okay, that is the idea. And once you have learnt f correctly on Lx, you can evaluate fx. So, f at Lx, if you evaluate this at x, you will get fx. So, that is what you output. So, the idea is simple. Let us now do the actual calculations and see what is the success probability and why does it work. So, let us do it formally. So, the input is you are given an x, it is a point in the space, you are given an oracle f tilde. Basically, you are given this oracle that will allow you to evaluate f at any point you like in the space. So, oracle f tilde that agrees with some an unknown L variate degree df. F on so as before lot of points, good fraction. So, on greater than 1 minus rho points. And what do you want in the output? In the output you want f of x. So, you want to output a field element which should be with high probability f of x. So, let us achieve that. So, the decoder is pick a random z, a direction, right. So, in this f to the L space. So, it is a random f to the L point you can think of, and define line Lx. So, x plus tz is the line, right. So, at t equal to 0 it is just x, at t equal to 1 it is x plus z, x plus 2z and so on. So, you can think of this as direction, this direction being z. Second step is query f tilde, which is corrupted version of f, query this on each of these points. On Lx, right, that is collect the pairs it's at field element t, look at the point x plus tz on the line and evaluate it. Evaluate it on f tilde. Right, so that is f tilde on the line. Okay, so on the random line but passing through x, you have computed f tilde. Now, how many of these pairs are correct? That is, they match with f. We later analyze that actually it's a good fraction, and so it makes sense to do Reed-Solomon decoding. So, via Reed-Solomon decoder, right, this is the actual unique decoder. It's not, we are not doing local decoding. So, use the Reed-Solomon unique decoder on f tilde Lx, and it will give you find a degree d polynomial q tilde. So, it will give you a univariate q tilde. Right. So, basically this has reduced the L variate question to one variate. That was the whole idea. And what is the property of q tilde? Such that q tilde t is equal to f tilde x plus tz for the largest number of t's. Right, that is the property satisfied by q tilde. And finally, output. So, if q tilde is the correct f on the line, then as you saw before, t equal to 0 is what we are interested in. So, you just output q tilde at 0. Okay, that hopefully will be the answer. So, let us just quickly observe that all this can be done in polynomial time. So, time is polynomial in L, D and the field size, because the Reed-Solomon decoder will work, and also the line computation will already take f, and in everything else it is polynomial time. Right. So, next we will do the analysis. So, it is clearly an efficient algorithm, but why would it work? Right, and we have to more importantly see that f of x value is outputted with a probability of at least 2/3. So, let us do that analysis. So, RS-decoder is trying to reconstruct the polynomial univariate polynomial qt, which is f of x plus tz. So, basically the q tilde is supposed to be qt, and we have to now check what is the chance that this actually happens, that q tilde is equal to q, right, because remember there is also corruption in f tilde, it is not really f, and if you pick an unfortunate line Lx, then you may get completely wrong answers, q tilde may not be q. So, it is clearly an efficient algorithm, but why would it work? right, and we have to more importantly see that f of x value is outputted with a probability of at least 2/3. So, let us do that analysis. So, RS-decoder is trying to reconstruct the polynomial univariate polynomial QT, which is f of x plus t z. But so basically the q tilde is supposed to be QT, and we have to now check what is the chance that this actually happens, that q tilde is equal to q, right, because remember there is also corruption in f tilde, it is not really f, and if you pick an unfortunate line Lx, then you may get completely wrong answers, q tilde may not be q. So, we have to analyze that. So, let us consider the probability over z, which is the random direction, that the number of t's with the qt not equal to q tilde t, which is f tilde x plus t z. Basically, once you have picked a direction z, you want qt to be correct on many t's, right. So, in particular the places where qt, the t's where qt is incorrect, you want that to be smaller than what Reed-Solomon RS-decoder can sustain. So, it should be less than f minus d by 2. Okay, so, number of t's should be smaller than half of the RS distance. That is what this is. So, half of RS distance. So, once this happens, once you have that this number of t's is smaller than half of Reed-Solomon distance, then Reed-Solomon decoder automatically, I mean as you saw before when we analyzed RS decoder, it will give you the correct Q, right. So, all you want to ensure is that this probability is high, it is at least 2/3. That is the question. Is this probability 2/3? And we will show yes. So, to show that, we consider the expectation of this. Okay, what is the expected number of t's that are bad over random z? So, the number of t such that f and f tilde do not match, these are the bad t's, right. So, number of bad t's expectation is at most, well, of course, at t is equal to 0 is one point which may or may not be bad. Let us just put 1 for that, plus the other t's in f minus 0, and for this t the expectation contribution is this is the probability of f and f tilde being different, right. So, let us put that probability here. not equal to f tilde x plus tz. Now, f tilde is a polynomial, f is a polynomial, I mean x and z are both fixed, right. So, both of them are univariate polynomials in fact. So, one variate, they are both one variate. So, they being different means that t is not a 0, but how do I get this information? So, here actually what you have to see is that x plus tz is a random point in the space, okay, because z you picked a random direction. So, actually that is what is important. This is a random point. Random point in f to the L. And once you realize that f and f tilde being different on a random point in space, that is given to you by rho. That is the probability upper bound. So, this is less than equal to 1 plus rho times size of the field minus 1. Okay, we remove t equal to 0 because that would have killed z. But for all other t's, z is there in x plus tz, and so this is really a random point. So, you have 1 plus rho times f as the expectation. Let us take that. So, now by Markov's inequality, basically it is just something simple. So, it is the following, that if the expectation is m, then what is the chance that in the random experiment the random variable takes value more than 2m or less than m by 2. Okay, so, both these the probabilities you can suspect already will be smaller than half. Okay, so, once you know expectation, you also have a good understanding of the probabilities that the random variable is too large or too small away from the expectation. So, in particular what you get here is that probability over z, that number of t where q and q tilde differ this number of t being larger than Reed-Solomon distance by 2, right. This will depend on how big f minus d by 2 is compared to the expectation. So, that is this probability is less than equal to expectation. So, 1 plus rho f minus 1 expectation divided by this f minus d by 2. Okay, so, the larger f minus d by 2 is, the smaller is the probability of being that much away from expectation. That is the idea. And let us now just do the simple calculation or simplification. So, rho is given to you by an upper bound, right, that rho is smaller than 1/6 of that distance. So, let us put that expression here, d plus 5 by f minus 1, let us put that divided by f minus d by 2, which gives you 1/3. So, that is it, that is what we wanted. So probability over the random direction, when you take a random direction, then the number of t's being bad t's being too many, more than half of the Reed-Solomon distance, that probability is at most 1/3. So for 2/3 of the choices, the Reed-Solomon decoder will work fine. So with probability over z greater than equal to 2/3, step 3, that's the RS-decoder produces Q tilde, gets Q tilde, which is actually Q is equal to x plus tz. Which further means, which obviously means that Q tilde 0 is equal to fx with probability 2/3. Okay, so that is the local decoder, handles errors up to 1/6 of the Reed-Muller distance. And what you should note here is that the number of queries is log of the length. Right, so this is really log of L plus D choose D. Or I should say F to the L. Okay, so it is polylog in the length of the code word. So hence it is fair to say that this is a local decoder. It makes very few queries and gives you one evaluation of F with 2/3 probability at least. Okay, so once you know local decoder for Walsh-Hadamard and Reed-Muller, the last thing is local decoder for the combination, the concatenation. For concatenated codes. So let instead of talking about Walsh-Hadamard and Reed-Muller, we'll just abstract it out and talk about concatenation of E1 and E2, where we know local decoders for E1 and E2. So let E1 be a code that is stretching n to m in alphabet sigma, so it's non-binary. Respectively, E2 is to make non-binary alphabet binary, so sigma 2 0 1 k. Be error correcting code with local decoders of Q1 respectively Q2 queries in the local decoder algorithm, and they handle say row 1 respectively row 2 errors. Okay, so we have abstracted it out. Of course, when you apply it to Reed-Muller, then sigma will be your finite field alphabet. E1 will be Reed-Muller, E2 will be Walsh-Hadamard, and these queries will be very few. But this is the setting. So now you want to show that the concatenation also has a local decoder. Moreover, we'll assume here that Q1 queries are at least that many as the alphabet. Assume that Q1 is at least the size of the alphabet. Now let us state the theorem statement. So the error correcting code E, which is first apply E1, go to non-binary, then come back to binary by E2. So it's a map that will stretch n to mk. This has a local decoder that can handle errors up to the product row 1, row 2. Okay. This is similar to what we did when we did unique decoding for the concatenated code. So you get the product, but more importantly the number of queries is small, remains small. So has local decoder this much with queries Q1 log Q1 times Q2 times log of alphabet size. Okay, so if Q1, Q2 was small, then this overall is quite small. Okay, this is just like product queries. So what is the idea? Given this corrupted y, so given y in 0, 1 to mk, break it into blocks of size k. And then think of these m blocks, each of size k, as these respective applications of E2. Okay, and use E2 decoder. So on a block, call E2's local decoder row 2 many times. So in that block you get actually the full string. Okay, you want this sigma. So log sigma times. So basically you will get these symbols. If you think of sigma as a field element, then you will get the full field element, and from that you can now move to even decoder to get the bit out of the local decoder. Finally, call even local decoder row 1 on several decoded blocks. Okay, so first apply E2's local decoder in a single block many times to get the full symbol, and then on these interesting blocks, some of the interesting blocks, you apply even's local decoder, and that will give you the information you wanted, the bit you wanted of x. So let us give the full algorithm and proof. So, input is index I, the bit you are interested in, Oracle access to Y, such that there exists a string n bit with the distance of Y from EX, this concatenated code word being small. Okay, so Y is corrupted but close to the code word, smaller than the product. That is the guarantee given to you. In the output you want Xi. So, a bit. So, decoder does the following, as already mentioned in the idea, that view Y as, now note that Y is very long, right? We are not actually working with the full Y. We are just doing this kind of implicitly or abstractly, and accordingly we will make the queries, but the queries in the end will be very few. Actual queries to Y locations will be few. So, that you can check in the end, each of k bits. So, it is basically a corrupted version of E2 applied on the symbols E1x. E1x has many symbols, right? It has m symbols. E1x has m symbols. So, this is the, let us say, the jth symbol. So, think of this, the jth block is basically a corrupted version of this. E2 of E1x is jth symbol, think of it as a field element, and when you apply E2 then it will produce a k bit string. So, first we will try to find E1xj completely. So, call E2's local decoder on the jth block of Y, do this log sigma. So, remember E1xj is an element in sigma, E1xj is a element in sigma. So, you need to which has then log sigma many bits. So, do this log sigma times to recover E1xj, that is the idea. But anyways, you will get some element in sigma by this. It may be correct, it may be incorrect, that we will see later. So, do this on the jth block, but you cannot do this for all j, right? Otherwise, you will be making a lot of queries that you do not want to do. So, which j will you use? So, repeat this let us say log q1 many times. So, what does E1 do? So, repeat these many times so that the probability of not decoding E1xj. So, the thing is that this E1xj may be incorrect, right, because the local decoder has its own error involved. It is already this 1/3 error is possible. So, you want to boost it down, we want to make the error smaller. So, let us repeat this experiment log q1 many times, so that the probability goes down to, let us say, 1 over q1, in fact 10 q1. Okay. So, log q1 repetitions would be enough, because this will already give you a small enough probability which you multiply with log sigma and still you get 1 over q1. And now what you do is, so E1 xj's are hopefully recovered for the j's we want, and now from E1 x we want to go to x, right. So, E1 is there were m symbols in the output of E1. So, out of those m we have to query q1 many, right, those are the j's that you are interested in. So, we need this. We need this because E1 local decoder will make q1 many j's. Right. So, the above experiment will run for a lot of j's, which is q1 many j's. So, we wanted the probability to be quite small compared to that. Now, let us move to E1's local decoder. So, what will that do? Before that, we have to give a guarantee of how many of these j's E2 worked correctly. So, we will do this next time. Okay, we will finish this local decoder next time.